not a prime, I bet.
Oh, hang on. I think the mics are still hot. Are we recording?
Looks like it. We were just getting into that spectral identity from episode 40, weren't we? The anti-superconductor thing.
Yeah, exactly. It's quite the rabbit hole. Well, apologies for the slightly chaotic start here, folks. But I have to say, this gunpowder coffee they have at the cafe today, it's something else. Really gives you that kick.
It absolutely does. And I find that chocolate latte provides the necessary counterbalance, a stabilizing influence against those caffeine peaks.
Huh. Stabilizing influence. I like that. Well, look, since we're already rolling and we've got that momentum from the arithmetic resistor discussion, maybe we just pivot. Let's jump straight into the next big idea. Are you ready for the prime walk?
Let's do it. It builds nicely on some of those ideas about underlying structure anyway.
Okay, great. So let's unpack this for everyone. Our mission today is, well, it's pretty ambitious. We're diving deep into this puzzle. Starts off deceptively simple, just a walk on a number line, but it somehow connects pure number theory to really fundamental concepts in physics. We're talking spontaneous symmetry breaking.
Exactly. We're essentially tracing this path, this number-theoretic random walk, and seeing how it mirrors almost perfectly the Jahn Teller effect. Which is, usually talked about in molecular chemistry.
Right, stability in molecules.
And we're using that analogy, that framework, to get a new perspective, maybe even sort of physical intuition, for one of the biggest mysteries in math, the Riemann Zeta function.
It's a fantastic core idea, isn't it? The possibility that the primes, these numbers that seem so random, so chaotic, might actually have this hidden order, an order governed by the same kind of rules that dictate, say, how a molecule settles into its shape.
That's the goal. We're using Jahn Teller as our sort of conceptual blueprint, translating the mechanics of prime factorization step by step into the language of physics, energy levels, stability, distortion. It's a powerful analogy.
Okay, let's dive in. Section 1. Setting up this prime walk puzzle and really understanding that core Jahn Teller analogy.
Right.
So first things first, let's lay out the rules. This isn't just any random walk like a drunkard stumbling around. The sources are quite specific, calling it the prime walk. How does it work?
Okay, the setup is pretty clean. You start at the origin, x equals 0, on an infinite number line. The sources like to call this the infinite hoops, metaphorically speaking.
Infinite hoops. Got it. And then
the process kicks off. A random natural number, let's call it n, is generated, picked uniformly from some large range or eventually from all natural numbers.
Okay, a random number n. And the crucial part, as I understand it from the sources, isn't just its prime factors like 2, 3, 5.
Exactly. This is the more advanced version of the puzzle, the one needed for the deep connections. You need to consider all the prime powers that divide n, not just the primes themselves.
Okay, unpack that. Give us an example.
Sure. Let's say the random number generated is n equals 12.
Okay, 12. Prime factorization is 2 squared times 3.
Right, so the distinct prime factors are 2 and 3. But for the walk, we need the prime powers. That's 2, which is 2 to the power of 1, 3, which is 3 to the power of 1, and 2 squared, which is 4.
Ah, I see. So the set of possible places to jump to based on n12 is 2, 3, 4.
Precisely. Those are your available destinations for the next step.
So if I'm sitting at some position, let's call it x sub t.
Your current location, yeah.
And I generate n12, giving me the options 2, 3, 4. How do I choose where to actually go? Which hoop do I jump through?
The rule is based on a minimization principle. You leap from your current spot, xt, to whichever of those available prime power factors, 2, 3, or 4 in this case, is closest to x on the number line.
Closest. Minimize the distance.
Minimize the distance. That closest prime power, pk2, becomes your new position, xt plus 1.
Okay, that makes sense. And this choice, this closest rule, this is where the symmetry idea comes in.
Exactly. Think about the very first step. You start at x, 0, 0.
Right at the origin.
Now let's consider the version where we allow moves to negative prime powers as well. So the destinations are potentially plus or minus pk2 dolls. If angle 4 is generated, the prime powers are 2 and 4. Let's just focus on 2 for simplicity. You can jump to plus 2 or minus 2.
Okay, and from 0, plus 2 and minus 2 are exactly the same distance away.
Precisely. The origin x0 is equidistant. It offers no preference. This means the starting state has reflection symmetry, x goes to minus x, and mathematically we call that state degenerate.
Degenerate. Meaning multiple options have the exact same cost or value, in this case, distance.
Correct. And systems in degenerate states are often unstable.
Right, because if the whole point is to minimize distance, and you have 2 equally minimal options, The system hasn't really minimized anything yet. It's like it's balanced on a knife edge, waiting for something to tip it one way or the other.
That's a perfect way to put it. It's the ideal setup for what physicists call spontaneous symmetry breaking. And this is where the Jahn Teller effect provides such a powerful physical analogy.
Okay, let's refresh everyone on the Jahn Teller effect itself. It comes from chemistry, right? Actual.
Yes, 1937,
Hmm.
Hermann Jahn and Edward Teller. It states basically that any nonlinear molecule that's in a highly symmetric geometric arrangement.
Like perfectly octahedral or something.
Exactly. And, crucially, also has a degenerate electronic ground state, meaning multiple electron configurations have the same lowest energy. That molecule is fundamentally unstable.
It can't stay that perfect.
It can't. To lower its overall electronic energy and become stable, it must spontaneously distort its own geometry. It changes its shape, elongates some bonds, compresses others, whatever it takes to break that symmetry and lift the electronic degeneracy.
So it chooses a less symmetric shape because that shape allows for a lower non-degenerate energy state. It sacrifices perfection for stability, like a copper ion complex squishing itself slightly.
Precisely. The distorted state is energetically cheaper. And the amazing thing the sources point out is that this physical principle is mathematically isomorphic to the prime walk's first step.
Yes, isomorphic, meaning they share the same underlying mathematical structure.
Exactly. The minimization of electronic energy in the molecule maps directly onto the minimization of distance in the prime walk. Let's map the components one-to-one. It makes it clear.
Okay, so the symmetric start, that's our initial position, pi sabor. It's degenerate because, say, +2 and -2 are equidistant, just like the highly symmetric unstable molecule.
Perfect. Now, the perturbation. In the JT effect, it's usually molecular vibrations or quantum fluctuations that shake the system. In the prime walk, it's the random number n and its set of prime power factors. That's the random input that destabilizes the perfect symmetry of X versa.
Right, the arrival of n forces a choice. And the move itself, jumping to the closest prime power, that's the minimization or distortion step.
Yes. You asked earlier why distance acts like a pseudo-energy.
Yeah, that threw me for a second.
Think of it this way. In any optimization problem, the thing you're minimizing acts like a potential or a cost function. The molecule minimizes potential energy, E. The prime walk minimizes distance, P k x t I. This distance is the mathematical potential that drives the system. Moving to the closest point is the walk's way of falling into the lowest energy well available for the factors of n.
Okay, that clicks. Distance is the cost function here. And the final piece, the symmetry break itself.
That happens the moment a choice is made. If N4 gave options 2, 4, and maybe N2 and X4 starting at X0, choosing +2 instead of X2 instantly breaks that X2X reflection symmetry.
The walk picks a side. It can't go back to being perfectly symmetric around the origin once it's moved.
Exactly. The symmetry is spontaneously broken by the first step, driven by the minimization rule acting on the random prime factors.
And the core insight here, the reason this analogy is so powerful, is that the same mathematical structure describes both physical stability via distortion, and this number puzzles initialization.
That's the claim. It suggests maybe number-theoretic structures aren't just abstract patterns, but they might also obey principles related to stability and minimal cost, breaking symmetries to settle into preferred configurations.
Before we move on, quick question. Why Jahn Teller specifically? Physics has other symmetry-breaking mechanisms, like the Higgs mechanism. Why isn't that the better analogy?
That's a really good point. The Higgs mechanism is about a field acquiring a non-zero value in the vacuum, usually breaking a continuous symmetry and giving particles mass. It's quite complex.
Right, involving potentials and fields.
The Jahn Teller effect is much more direct and arguably simpler in its core concept. It's about lifting a degeneracy, distinct states having the same energy or cost in a system, often discrete, by distorting it. The prime walk at X here presents a simple degeneracy in position, plus pk versus diff pk having the same distance. JT is just a cleaner, more direct fit for this specific puzzle's starting mechanism. It's about choosing between discrete, equally good options.
Okay, that makes sense. JT fixed the specific degeneracy at XCO better. All right, so the symmetry is broken. The walk has taken its first step. Now what? How does it behave long term?
Now we need to model its dynamics. And the natural way to do that is as a Markov chain.
Okay, Markov chain, meaning the next state only depends on the current state, not the history.
Exactly. The states of our Markov chain are the possible locations, the positive prime powers, pk. For now, let's imagine we put an upper bound, a large number n, just for analysis. So states are pk-doba.
And the transitions between these states,
Yeah.
that's determined by the random number n again.
Entirely. At each step, you generate a new random n, Find its prime power factors, pk dollars, and jump from your current state, say 6 doll, to the pk factor that's closest. That defines the transition probabilities.
So we need to figure out the probability of being able to jump to a specific state, pk dollars. That means pkl has to be a factor of the random n generated at that step.
Precisely. And this is where a fundamental piece of number theory comes in. If you pick a random integer n from a large range, up to some very large n, the probability that a specific prime power pk divides n is approximately
1 over pk.
exactly ppk tech divides n approx 1 pk da. This simple relationship is the engine driving the walk's behavior.
Wow. Okay, so that single fraction, 1 pk dollar, basically dictates the whole long-term bias of this walk.
It really does. Look at the numbers. The probability that 2 divides n is about 12.
50% chance, roughly.
The probability that 3 divides n is about 13. That 4 divides n is 14. The probability mass is hugely concentrated on the smallest prime powers.
While the chance that, say, $312 of his 961 1 divides n in is only about 1 in 961. Tiny.
Extremely tiny. So if you think about the transition matrix for this Markov chain, the grid, showing the probability of going from any state I to any state j, it's going to be incredibly dense for transitions involving small numbers like 2, 3, 4. They're accessible from many places and lead to many places because they divide numbers so frequently.
Whereas transitions involving big prime powers like 961 are going to be very sparse. They're rarely available as destinations.
Exactly. It's a highly asymmetric network. The small numbers are major hubs. The large numbers are remote outposts.
But, and this seems crucial, those probabilities, like 1961, are small, but they're not zero.
Critically non-zero. And this leads directly to the concept of ergodicity, which we can understand by looking at the opposite probability.
The probability that pk text is not divide m prox 1 tki, then a particle is always greater than 0 for any prime power pay. This complementary probability, 1 pkr, is always strictly less than 1.
Okay, what does that guarantee? It guarantees two fundamental properties for any finite bounded version of this walk, up to n. First, irreducibility. Because there's always some chance pk dollars being a factor, and the closest rule length states you can eventually get from any prime power state to any other prime power state. Maybe not directly, but through some path.
So the walk isn't trapped in separate sections of the number line. It can, in principle, reach anywhere.
Correct. And second, it guarantees ergodicity. An irreducible Markov chain on a finite state space is always ergodic. This means the walk doesn't just reach every state, but it will visit every single prime power state $80 infinitely often if you run it long enough. It explores the entire space.
And how does this connect back to the Jahn Teller idea?
Well, the JT effect describes distortion to a stable minimum. But often, a molecule might have several equivalent distorted shapes it can adopt. Ergodicity here is like saying the system doesn't get permanently stuck in the first minimum it finds. It can still explore the entire landscape of possible stable configurations of prime powers. The non-zero 1 tk dollar probability ensures the whole potential energy surface of the prime powers is accessible.
So it breaks the initial symmetry, finds a stable spot, likely a small pk do, but it's not locked there forever. It keeps exploring.
Exactly. It's constantly sampling the arithmetic landscape. And we can see this very clearly in simulations. If you run this walk for, say, millions of steps with a bound like in 1000, you can calculate the stationary distribution. That's the long-term probability of finding the walk at state pk.
And the results really show that bias towards small numbers, right?
Absolutely. The simulation data is striking. The top visited states completely dominate. State 2, pp2 is visited roughly 22.1% of the time. State 3, pp3 k once is visited about 14.9% of the time. State 4, pp2 k is visited around 9.9% of the time.
Wow, look at that. State 4, 202 powers, is visited more often than State 5, which would be around 15 or 20% if it were just 1 dealers, but other factors reduce it. It really shows it's 1 TP tollers weighting small bases and small exponents.
Precisely. 40 tollers is bigger than 50 tollers. That on pk tollers governs everything. This concentration near small prime powers is the walk's preferred low-cost region. But now, look at the tail.
We need to see if those big remote states ever get visited to confirm the ergodicity claim.
Let's take $312 as 601 PLR. It's near the edge of our N1000 bound. The simulation shows its stationary probability is tiny, something like 10 4 or 1, or 0.01%.
Small, but definitely not zero.
Definitely not zero. So while it's rare, the walk will eventually land on 961. It confirms the walk is ergodic within this bound. The entire arithmetic terrain is connected and visitable.
Okay, but what about the overall behavior, the average position? Does that tell us anything?
It does, mainly by being misleading. For N1000, the calculated expected position, the average value of the state visited, is around 120.45.
Okay, 120. Seems reasonable.
But the standard deviation is huge.
Yeah.
It's calculated to be around 249.
Wait, the standard deviation is more than double the mean. What does that signify?
It signifies that the walk spends almost no time near its average position of 120. A large standard deviation relative to the mean points to a distribution with heavy tails or extreme values. Here, it confirms what we suspected. The walk overwhelmingly hangs out near the small prime powers, 2, 3, 4, etc., clustering close to the origin.
But then, occasionally,
A random n comes along that happens to be divisible by a large prime powers like 961, and maybe 961 is the closest factor to the current position. So whoosh, the walk makes this enormous leap far out onto the number line.
and those rare leaps dramatically inflate the calculated average and especially the standard deviation.
Exactly. It paints a picture of highly localized chaos, mostly hovering, punctuated by sudden, large, infrequent jumps. The walk maintains its stability by constantly returning to the gravitational pull of the small, common arithmetic structures. But the possibility of large jumps keeps the long-term average surprisingly high and volatile.
Okay, that makes sense for the finite case, but the real magic happens when we let n go to infinity, right? The unbounded walk.
Yes. Now we transition to the infinite journey. The state space becomes all prime powers, $, and the focus shifts from a stationary distribution, which we'll see doesn't exist, to the nature of divergence.
This is where it connects directly to the Riemann Zeta function, I believe.
Absolutely. To understand the infinite walk, we need to consider the total weight or mass of all possible states. This is like trying to normalize the probabilities. We calculate z, the sum of all the 1pk probabilities.
So z, sum textile, 1pk.
Right. And as we saw before, we can group this sum by the prime base. For each prime, we get a geometric series. Sum p 1p plus 1p2 plus 1p3 plus problem.
Which sums to $1p1 for each prime.
Correct. So the total weight of the infinite walk is z sum p Nash's 1 prime.
And this sum, this is known to diverge. It goes to infinity.
It diverges. Z rate arrow in 50 to 50. This is a fundamental result. Because the total probability mass is infinite, you can't actually define a normal stationary probability distribution that sums to 1.
So what does that mean for the walk, if there's no equilibrium state?
It means the walk is what's called null recurrent. It's still ergodic. It will still visit every single prime power pk dollar, no matter how large, infinitely often if you run it forever.
Okay, still visits everywhere.
But the expected time to return to any given state becomes infinite. The walk is guaranteed to drift further and further out towards infinity. It never settles down.
And this divergence, this infinite sum z, is directly related to zeta.
It is the essence of the pole of the Riemann zeta function at S1. Remember the Euler product definition of zeta? Zeta said.
Right, the product over primes.
If you formally expand that product, it generates the sum over all integers, sum into n packs. When you set S1, you get the harmonic series, sum of 1 back, which famously diverges to infinity. Our z-sum, sum 1p1, is capturing the prime power contribution to that divergence. It's like the walk is dynamically enacting the Euler product at its point of divergence.
It's Zeta's prime factorization theorem in motion, as the source material puts it. The walk's tendency to drift infinitely reflects Zeta's pole at S1.
Perfectly stated. But the way it diverges is just as important. It's not a rapid explosion to infinity.
It's slow, right? You called it the harmonic crawl.
Even slower than the standard harmonic series. We know the harmonic series 6/0 pill by 1pk diverges like the natural logarithm, which is already quite slow.
Yeah, log growth is slow.
The prime power sum, the x1pk, diverges double logarithmically. Its growth is asymptotic to 1 ln x plus c, where c is a constant around 1.034.
Double logarithmic. That sounds incredibly slow. Can we quantify that difference? Make it tangible for someone listening?
Absolutely. Let's use the example from the sources. How many terms x do you need for the sum to reach a modest value, say 10?
Okay, for the standard harmonic series, SXX approx ln x6. So we need x approx 10. That means $6 is roughly E10.
And E10 is about 22,000. Manageable. You could compute that.
Now for our prime power sum, Zecatrox ln x plus 1.0344. For Zekatson ups to reach 10, we need 8 lowing x approx 10, 1.0343. That means 8.9666.
Okay, first step. What's $8.906C6? That's about 7 and 937.
So all x dex needs to be 7 and €37. That means x itself needs to be 837x.
The A6 grows $7 and 804 zeros.
The number of atoms in the observable universe is estimated at 10. This number is just incomprehensible.
Completely beyond physical reach. And that's the point. This is the implication for the infinite prime walk. Yes, it drifts to infinity. 6 to right in 50 almost surely, meaning with
Oh.
probability 1.
Yeah.
Yes, it visits every prime power infinitely often. It's ergodic.
Yeah.
But it does so at this extraordinarily slow double logarithmic pace. The Julian x crawl means the walk spends an almost unimaginable amount of time lingering near the small prime powers 2, 3, 4 before it makes significant progress toward exploring the larger ones. It's perpetually drawn back to that low-cost, high-probability region near the origin.
So let's put this back into the Jahn Teller analogy. The walk breaks symmetry at Augusta distorts to find a stable state, like 2 or 3. And
Then it begins this incredibly slow drift along what you could imagine as an infinitely long, almost perfectly flat valley or trough in the potential landscape, the famous Mexican hat potential idea, but stretched infinitely. The divergence means it's always exploring new territory, new prime powers, new distortion modes. But the Jahn slowdown ensures it never truly escapes the influence of the most fundamental, most probable structures.
it's an eternal crawl, always moving forward, but barely making progress relative to the infinite scale it's exploring. A system forever exploring, but forever bound to its origins.
That captures the essence of null recurrence, driven by double logarithmic divergence.
All right, we've used the walk and JT to understand factorization, probability bias, and even Zeta's pole at S1. Now for the grand finale. Applying this whole conceptual framework to the Riemann hypothesis itself, the location of Zeta's non-trivial zeros.
This is where the analogy becomes perhaps most speculative, but also most tantalizing. We start again with symmetry. The Riemann zeta function has a fundamental symmetry encoded in its functional equation.
Zeta is some complex factor involving gamma functions and pi.
Right, but the core relationship is that the value of zeta at CO is directly related to its value at $1 in this zeta. This equation forces a reflection symmetry across the vertical line in the complex plane where the real part is 12. The critical line, operator name 12T2.
So the critical line is like the initial point of high symmetry. It's the equivalent of exos in the prime walk, or the perfect unstable molecule in the JT effect. It's the degenerate state.
Exactly. That's the baseline symmetry. Now, what acts as the perturbation? What destabilizes this symmetry?
It has to be the primes, right? They're the building blocks.
Precisely. If you look at the logarithm of the Euler product, sump log EBSS, and expand the logarithm, you see terms involving primes and their powers. These primes act like the vibrational modes that perturb the perfect symmetry defined by the functional equation.
Okay, so we have a high symmetry state, the critical line's reflection property, made unstable by perturbations, the primes. What does the Jahn Teller principle demand happens next?
It demands the system must distort itself to find a stable, lower energy configuration. It must break the symmetry. In the context of the zeta function, the stable configurations are naturally interpreted as the points where the function goes to 0, the non-trivial zeros, 2 ordinators. These are the ground states of the function's potential.
So the zeros are the result of the function settling after being perturbed by the primes. But the JT effect also said something about residual symmetry, didn't it?
Yes, crucially, when a system distorts via JT, it lowers the symmetry, but it often retains some subset of the original symmetry elements. It doesn't usually become completely asymmetric.
So what's the residual symmetry for zeta?
It has to be the critical line itself. The functional equation zeta isn't broken by the primes, it's an inherent property. It mandates that the structure of zeta remains symmetric around operator name 12. So while the primes force the function to develop zeros, the distortions, these zeros must arrange themselves in a way that respects the reflection symmetry across the critical line.
And the only way for zeros to respect that reflection symmetry is if they lie on the line itself.
That's the simplest, most direct way. If a $1 is on the line, its reflection $1 is on the line, its reflection $1 is 112, it's just its complex conjugate, which is also known to be a zero. The set of zeros on the line is perfectly symmetric with respect to the line.
But what if a zero were off the line, say at sigma plus it will, where sigma is not 12?
Then the functional equation demands that $1 sigma in a dollar must also be a zero. You'd have zeros occurring in pairs mirrored across the critical line, but not lying on it.
And in our JT analogy, what would that represent?
That would represent a distortion that failed to preserve the mandatory residual symmetry. It would be like the molecule distorting in a way that's energetically extensive or unstable because it doesn't align with the underlying constraints. It's a less economical way to break the symmetry.
So the Riemann hypothesis, the statement that all non-trivial zeros are on the critical line, becomes, in this JT picture, a statement about stability. The zeros lie on the line because that's the lowest energy, most stable configuration that simultaneously lifts the degeneracy, makes the function zero, while preserving the required reflection symmetry.
That's the essence of the heuristic. It suggests the observed location of the zeros isn't just a mathematical curiosity, but potentially a consequence of the system finding the most stable or cost-effective way to accommodate the perturbing influence of the primes while respecting the functional equation's symmetry. It breaks symmetry just enough by having zeros off the real axis, but preserves residual symmetry by keeping them on the critical line.
And the specific locations, the imaginary parts of the zeros, 14.13476, 21.02210HO, 25.010109011.
In this analogy, you could think of those imaginary parts as being related to the frequencies or energy levels of the allowed distortion modes, fundamentally determined by the prime number distribution itself. They represent the spectrum of stable configurations.
That's really quite elegant, connecting molecular stability from 1937 directly to this huge unsolved problem in number theory. Okay, this feels like a natural point to maybe tie things together, perhaps with that final piece you mentioned from recent research.
Yes, let's bring in that 2025 update concerning the Bohr-Jesson limit theorems. It adds another layer to this idea of symmetry and chaos.
Bohr-Jesson. What do these theorems tell us, broadly?
They deal with the value distribution of zeta functions, including generalizations like Epstein zeta functions, which relate to lattices. Essentially, they describe the probabilistic or statistical behavior of these functions in the complex plane. They show that the values behave chaotically, but follow specific probability distributions.
Okay, chaos, but with underlying statistical rules. How does that relate to our prime walk and symmetry?
The recent work focuses on the partial products of the Euler product, like prob p, luck, 1 ps, 1 ash, 1 nix. These are finite approximations to the zeta function. The research shows that while the values generated by these partial products exhibit chaotic behavior and phase transitions.
Phase transitions, like symmetry breaking.
Exactly. Symmetry breaking occurs, especially around the critical line or related thresholds, often denoted beta tilde in these studies. But crucially, the statistics show that even within this chaos, a fundamental symmetry related to the critical line, often called half-center symmetry, is preserved probabilistically in the limit.
So even though locally things look chaotic and symmetry might seem broken, like the prime walk taking its first step off zero, the overall statistical distribution of behavior must conform to the underlying symmetry dictated by the functional equation.
That seems to be the message. The prime walk, driven by the Long-Peyk-Kendall probabilities, enacts the local symmetry breaking. But the very probabilities driving it are derived from the primes, whose collective behavior, as encoded in zeta, is statistically constrained to respect that operator symmetry in the long run. The chaos isn't completely unconstrained. It operates within bounds set by the function's core symmetry.
So the walk drifts, it explores ergodically, it diverges double logarithmically, but the pattern of its exploration, the frequencies of visiting different regions, is statistically shaped by the need to uphold zeta's symmetry.
That's a compelling way to synthesize it. The JT analogy captures the local break, the algebraic divergence captures the infinite exploration dynamics, and the probabilistic limit theorems suggest that even this infinite chaotic exploration adheres to a deep residual symmetry on a statistical level.
It beautifully ties the start of the walk to its infinite behavior and the structure of the zeros. Stability isn't about being static. It's about finding the dynamic equilibrium that respects the system's fundamental constraints.
Whether it's a molecule finding its shape, the prime walk crawling towards infinity, or the zeta zeros aligning on the critical line, the principle seems remarkably consistent.
This has been absolutely fascinating, a real deep dive. We went from a simple number line puzzle move to the closest prime power all the way through spontaneous symmetry breaking using the Jahn Teller effect. We saw the ergodic nature of prime factorizations through the quant PK probabilities, uncovered that incredible double logarithmic divergence, the harmonic crawl,
and landed on a powerful, physically motivated heuristic for why the Riemann hypothesis might be true, seeing the zeros as stable distortions respecting residual symmetry.
It really underscores how connected these different fields can be. What's the final thought you want to leave our listeners with today?
I think it comes back to that infinite walk and the divergence. The prime walk really hammers home that stability in many fundamental systems might just be a long-lived approximation. True long-term behavior, whether in physics or number theory, might be governed by this kind of eternal, incredibly slow dionic divergence. A constant exploration that never truly settles, but is always constrained by underlying rules. It makes you wonder, how many other complex, seemingly chaotic systems out there, maybe in economics, biology, cosmology, might secretly be following this incredibly patient, double logarithmic crawl towards some infinite limit, constrained by hidden symmetries we haven't fully recognized yet.
That is a profound thought to mull over. Thank you for guiding us through that incredible journey. And thank you all for joining us. Hopefully you got a good mental workout thinking about these primal walks. If you're interested in the probabilistic side, definitely check out those Borges and limit theorems.
Indeed. Keep exploring.
We'll catch you on the next deep dive.